Hi, and welcome back to our chemistry flipped classroom. And today we're continuing our discussion about bonding by talking specifically about ions and ionic compounds. So obviously our positively charged ions, which we call cations, are going to be attracted to our negatively charged ions. And so we're going to see this force of attraction, and that's what we call an ionic bond. So today we're going to just have a quick refresher of the periodic table and how we use it to predict which ion a given element forms. But we're also going to connect that to electron configuration and understanding how the formation of an ion really creates a pseudo noble gas configuration. And then finally, we're going to be talking about the size of ions relative to other ions and relative to what we call their parent atoms, so the atoms that they come from. So just that quick reminder of the octet rule, and generally speaking, with our main block elements, we say that ions form so that atoms, by either gaining or losing electrons, have that pseudo noble gas configuration. They have 8 electrons in their valence shell, their outermost shell. So they have a filled s orbital and a filled p orbital. So that means because metals have just a few electrons, mostly in their s and sometimes in their d orbitals, are going to lose electrons to form positively charged cations, and our nonmetals are going to gain electrons to form negatively charged anions. So when our metals form ions, their noble gas configuration, their pseudo noble gas configuration, remember pseudo means fake, so our fake noble gas configuration is going to look like the noble gas that comes before that metal. But when our nonmetals form ions, their pseudo noble gas configuration is going to look like the noble gas that comes after, because they're gaining electrons. Okay, so we know how these go together. We know that they form so that we have 8 valence electrons. And then we know that those positive and negative charges then create a really strong electrostatic attraction, and they create the crystal lattice. So let's talk a little bit about what we call a crystal lattice. So unlike molecules where we have a predetermined number of atoms that join together, so water is just 2 hydrogen atoms and 1 oxygen atom. When we have ionic compounds, it is a lattice. So you can think of this as like a network of positively charged ions surrounded by negatively charged ions, and negatively charged ions surrounded by positively charged ions. So we have all these attractive forces. So if we're looking just at the end here, so this would be our cation, and we'll explain how I know that in a little bit. So our cation here, you can see that there are 4 anions around it. And if this were to come out in the dimension towards us, there would be another one in front, and there is another one behind. So every negatively charged ion is surrounded by 6 positively charged ions, and every positively charged ion is surrounded by 6 negatively charged ions. So that means that we have these crystals with these very regular ordered structures, and we have alternating positive and negative ions. So remember, in chemistry, we use the term salt to describe any ionic compound, and all salts form crystals. Generally speaking, the higher this lattice energy is, the energy that is released when these ionic bonds form, the higher the melting point of our ionic compound is going to be. And this is why ionic compounds have such high melting points, because they have all of these bonds, and in order for them to melt, unlike molecular compounds, we actually have to break those bonds. And we'll talk about that more later on. So we've already talked a little bit about ionic character, and we've said that we use a shortcut that if the difference in electronegativity is more than 1.7, we say that that's an ionic bond. But you might remember that I said that that's kind of our shortcut, our general rule. It's not hard and fast. So how we truly determine whether or not something is ionic is that if it is in its liquid state and it conducts electricity, then it's an ionic compound. So anything that does not conduct electricity in its molten state or its liquid state is not an ionic compound. So HF as an example, so hydrogen fluoride, has an electronegativity difference of, let's see, it's 1.9. So by our rules, that would say that that's an ionic compound, but we find that if we have liquid hydrogen fluoride, it does not conduct electricity. So we know we don't actually have ions, and the reasons for that are kind of beyond this course, but this is our absolute definitive answer. When it is in the molten state, it conducts electricity, it is ionic. Okay, so let's talk about ion sizes. So we talked about atomic sizes, atomic radii, and we said that as we go across the periodic table, the size of the atom decreases. And that's because we're adding more protons to the nucleus without adding any energy levels. And so it's drawing the electrons ever tighter. So when we think about a cation has more protons than electrons. And so that means that it's going to be pulling even more tightly on those electrons. And so cations are always going to be smaller than the atoms that they come from, than their parent atoms, because those outermost electrons are removed. We actually lose an energy level. The repulsions between electrons are reduced and the attraction to the nucleus is increased. And so we get a smaller ion. So cations are always smaller than their parent atoms. On the other hand, anions, because we're adding more electrons, are going to have increased repulsions. And so they're going to be larger than their parent atoms. We have the same number of protons in the nucleus, but more electrons. And so they're always going to be larger than their parent atoms. So if we go back to this image of our crystal lattice, and I said I knew that this was our cation and these green ones were our anions, that's because the cation is going to be smaller than the anion. So back to sizes of ions. So we can compare atoms to their parent, ions to their parent atom, and we know cations are always going to be smaller, anions are going to be larger. We can also compare what we call isoelectronic ions. So isoelectronic means that they have the same number of electrons, not the same number of valence electrons, but the total same number of electrons. And so if we look at the sodium ion, the magnesium ion, the aluminum ion, the oxygen ion, and the fluoride ion, they all have the same number of electrons, which is to say 10. So as the nuclear charge increases, so the number of protons in the nucleus increases, the ion size decreases. So fluorine has more protons than aluminum, and so it is, I'm sorry, said that backwards. Aluminum has more protons than fluorine, and so it is smaller. Okay. And this is just a table of those ion sizes. So within an isoelectronic series, we have decreasing size with increasing nuclear charge, and cations are smaller than their parents, anions are larger than their parents. And that wraps it up for ions and ionic compounds. As always, if you have questions, I look forward to seeing you in class.